Hello, we're recording live. So I'm going to tell you two things. First, we're going to remember how do you define a logarithm, and then how does a logarithm make intuitive sense. And then we're going, we just finished looking at identities for exponents. Let's now look at identities for logarithms. Every single identity for exponents has a corresponding identity for logarithms, which shouldn't be surprising because exponents and logarithms are inverses. Okay, so let's remember what are logarithms about. So I'm gonna review it by way of an analogy. So if I have this number, fifth root of 2, this thing describes a single number. So you might think about this as an operation being applied to a number, but I think about this thing as a single number. So if you want to know which number is it, I would say this is the number that gives you 2 when you multiply it by itself 5 times. Does that make sense? This is this thing in the blob is the number that will give you 2 when you multiply it by itself 5 times. So, one way of writing that is, let's take this number and give it a name like x. So if I want to know what is x, what number is this x, this description, I just told you that x times itself 5 times gives you 2. And you can kind of see algebraically that these are equivalent, because I could raise both sides here to the power of 5 and I get this, and then I take the fifth root of both sides and I get that. But I wanted to show you that the algebra actually kind of has an intuitive underlying meaning, which is about what fifth roots are about. So here's the analogy. So this is a number, and the number is describing a relationship between 5 and 2. So let's look at logarithms. If I have log base 7 of 50, don't think about this as an operation being applied to 50. This itself describes a number with a very special property. What number is it? It is the number that gives you... It is the power of 7 that gives you 50. So, in other words, if I'm going to give log base 7 of 50 a name, like x, I'm saying that 7 to the power of this number, 7 to the power of this, is going to give us 50. 7 to the power of the power of 7 that gives me 50 gives me 50. So that's the intuitive way that logarithms make sense. And you can even often kind of guess what they are based on that. So log base 7 of 50, I know 7 squared is 49. So if this is the number, if this is the power of 7 that gives me 50, I know that it's going to be slightly larger than 2. Because if 2 is my exponent, it gives me 49. I want the exponent that gives me 50, so I know that that's going to be slightly bigger than 2. So you can use that idea to kind of reason intuitively. So in terms of a definition, we would say log base a of b equals c. You can re-describe as an exponent by saying the number on the left is what power of a would give you c. C is the power of a that gives you b. I think that's the best way to put it. So a to the c power gives you b. So you can go back and forth between those. All right, so let's talk about identities now. Let me scoot this down a little bit. So you already know this identity. A to the b times a to the c equals a to the b plus c. And that is an identity of exponents. So there's an equivalent logarithmic identity, log base k of m times n equals log base k of m plus log base k of n. Okay, so wait, first I want to kind of notice some similarities here. So if you think about the equal sign as meaning the left hand and the right hand sides are interchangeable, what that means is that I can take two exponential terms multiplied and turn them into one exponential term where you're adding inside. This is sort of similar here, except reverse. Here I've got one logarithmic term where I'm multiplying on the inside, and I can turn that into two logarithmic terms where I'm adding on the outside. So in both these cases, I've got like a multiplication turning into an addition. Multiplication turning into an addition. But here I'm multiplying on the outside of the exponential terms, and then the addition is on the inside of the exponential term. Here I'm multiplying on the inside, and the addition is on the outside. So all I'm trying to do is like point out some similarities right now. Okay, well, so I just told you that this thing on the right-hand side is true, but like, how do you really know it's true? Because logarithms and exponents are related, you should be able to turn this one into this one, or you should be able to use this one somehow to justify that that one works. So that's what I'm going to show you right now. This is a strategy for proving an identity. So here's how the strategy works. Step one is I want to be able to turn these two terms separately into exponential terms. So I'm going to rewrite them. And this is sort of similar to the blob method. I'm going to name this term x. So x equals log base k of m. And x is just, yeah, I could name it anything. I could call it p, I could call it q. I'm just trying to give a shorter name to this expression. And then this one, let's call y equal to log base k of n. So what that means is now I can like rewrite this right-hand side to be just x plus y. Okay, so remember, what does it mean to prove an identity works? We're asking the question, are these two sides the same? And in order to show that they're the same no matter what, we would need to do some algebra on the left-hand side in order to show that, like, yes, these two sides are really the same no matter what. So that's what we're hoping to do is justify using algebra that they actually are the same, even though they look different. Okay, does anybody see how to do it? Here, I'm going to pause the video. Then, okay, here I am back in the video. So if we want to be able to simplify this side, I want to get rid of the log somehow. And I know I could get rid of the log if I said like log base k of k to the something. Like that would let me eliminate those. So that's kind of what I want to do. I need to turn m times n into like k to the something because I know that would let me do the cancellation. So what that tells me is I need to turn m and n into something having to do with exponents. So let's try and work with with our original definitions here and turn them into exponentials. So I can apply the definition of a logarithm to each of these to get x to get k to the x equals m and k to the y equals n. And hopefully it's kind of clear why I can do that. So what that means now is I can substitute in for m and n. So now I know that m is the same as k to the x, n is the same as k to the y. Aha! Now I can use the exponential identity. So now I know that this is the same as x plus y, k to the x plus y. And log base k of k to the anything, like those log base k and k to the whatever power, those are undoing each other because they're inverses. And so now I've just got x plus y. So I had x plus y on the left, I've got x plus y on the right. In between, I only did algebraically valid moves that don't change any values. Like these moves in the middle are true for all values of x and y and m and n and k and so on. So I have now shown that even though at the beginning, if I asked you without telling you, like, is the left-hand side the same as the right-hand side? You have no idea because, like, they look really different. But now we've shown that actually if you manipulate it a little bit, you can see that they are the same no matter what. And so now we've proven the identity. So that's the general strategy. Here, let me pause the video one more time. So the overall strategy you want to remember here is turn your logarithmic terms into exponential terms. And the way you can do that is by defining new variables. You can give this term a name like x, give this term a name like y. Now you can apply the definitions to turn them into exponential terms. And then you can use your exponential simplification properties to derive the identity having to do with logarithms. So in short, make the logs into exponents, and then you go. And that's what you'll be doing next week.